Hello, I'm very honored to give this keynote address at this conference. I'm Per Stenström and I'm going to talk about towards data-centric computer architectures. So the first what I'm going to do is to talk about technology trends for building computer systems, okay? Then I'm going to focus on a couple of ways that one can improve architectures when it comes to data-intensive applications. And one topic that I've spent a lot of research on is applying compression techniques to the memory system. The second topic I'm going to talk about is also related to quite recent research in my lab, and that is that how we can expose the cache hierarchy to software to improve on the efficiency of the memory system. Final topic is going to be my glimpse about the future and towards data-centric architectures, and especially talk about a recently launched project in my research lab before I conclude. So let's look at the current trends in computing. So for quite some time now there's been a shift from compute to data-centric computing, and that's driven by a lot of applications that typically where we have to analyze large data sets. One, of course, very important application where this becomes an issue is for machine learning, where we basically have to analyze large, growing size of the machine learning models, okay, when it comes to training, and then, of course, do inference on large data sets as well. But there are also other applications where actually that are very data-centric, and those are graph algorithms. So if we look at actually the way we have built computers for many decades now, is actually it goes back all the way to what is called the first electronic computer, the ENIAC, where there was separation between memory and compute. And this way of building computers to have a separation between compute and memory still holds for computer systems, where we have the microprocessor chip, and then off the chip we have a growing amount of memory, okay? The problem with this, what we call the von Neumann bottleneck in the context of data-intensive applications is the following. First of all, this has been a very productive model for the compute-centric era, when there was a lot of, most of the time was spent on actually doing computations on quite limited set of data. And also, even with a growing set of data, many applications exhibit data locality. So that means that on-chip caches have been very effective. But nevertheless, there is this speed gap blocker that it actually, the ratio of time it takes to access the memory versus doing, for example, a floating point operation is in fact 2 orders of magnitude. So when data is not found in on-chip caches, we have to go all the way off-chip, and that takes 2 orders of magnitude longer time than doing an arithmetic or logical instruction operation. But it doesn't stop there. What has also happened is that as compute performance increases, then actually the need for higher, we need proportionally higher memory bandwidth. And the problem is that the microprocessor chips are pin limited. So we are actually running into a bandwidth wall, you could say. And third problem with this paradigm of compute-centric paradigm is actually the difference in the amount of energy expended when doing a floating point operation versus going again off chip to memory. It's actually 3 orders of magnitude more energy to go off chip to fetch, data in the off chip memory versus what is expended on doing a floating point operation. So all these things are huge challenges as we move forward, and especially in the context of having applications more and more data intensive. So a new computing paradigm is definitely needed. So if we look at technology trends, the power of scaling laws is actually disappearing. The first law that actually stopped working was what we call Denner scaling. Denner scaling actually meant that we could increase the clock frequency, but within a certain power budget, so the power consumption didn't go up. And the trick that was played was actually to reduce the voltage as we increase the frequency. And since voltage square times frequency is actually how power consumption scales, then one could keep actually power consumption constant on the chip. But that worked until 2002, and the reason why it couldn't work after that is that we had decreased the voltage to a level where transistors started to leak, and so energy efficiency became a first-class citizen. So the only scaling law that actually was left was Moore's law, meaning twice as many transistors about every other year. And that led to that we went to multi-core systems, so that with each new technology generation the hope was to double the number of cores. But now even Moore's law is losing steam, meaning that technology scaling doesn't work so efficiently anymore. So we must rely on architecture and software optimization from now and on, which makes computer architecture a very important playground for seeing higher efficiency of our computers. What are the implications then on the memory systems? Well, capacity scaling is tapering off, so there is a memory capacity limit. Since memory chips, of course, also has followed Moore's law, and we don't see Moore's law as effective anymore, there will be a memory capacity limit. And PNIO has also reached the limit, so there is a memory bandwidth limit. And of course, industry is tracking this and coming up with new technologies like CXL, disaggregated memory, where we actually pool the memory. That can, of course, help in the short term, but in the long term, there will be a problem. So that takes me to the second topic here, remove the waste, compressed memory. So how can we help making memory systems more effective by actually using compression technology? That is a research topic that I have been working on for now almost 2 decades, that has led to an interesting startup company, 0 Point Technologies, that I'm going to talk a little bit about too. So let's look what is under that umbrella. So here we have a simple diagram of a multi-core system, you could say, with a multi-core chip to the left, which has a number of cores, denoted P here, each connected to a private L1, L2 cache. and all of these cores with their private caches are connected to a shared L3 cache. So that's a typically, you know, how you Intel and AMD and others build their chips today. And then you have typically a memory controller that reaches out to the off-chip memory and the disk. There are a couple of problems with this basic architecture, and that is that since Moore's law is not scaling anymore as effective as it was, then of course we will not be able to scale up the size of the caches. And in fact, as we double the number of cores, we need basically twice as much cache on the chip. So that is one challenge. The other challenge is, of course, that the bandwidth is we are kind of, you know, using up all the available memory bandwidth. And the third problem is that memory capacity, off-chip memory capacity, doesn't scale. So if we thought about having all the data compressed in both off-chip memory and in the caches, then we could improve utilization of both caches and memory, and that could improve the latency problem. And not only that, we could also, since we could make the L3 cache substantially larger, we would cut down on the memory traffic, actually improving the effective memory bandwidth, and also the energy efficiency, as we don't have to go out to the off-chip memory so often. So that's the opportunity here. So let's see a little bit how whether such an approach would work. So just as a recap, caches have relied on reference locality, which comes in two flavors: temporal reference locality and spatial reference locality. What temporal reference locality means that if we access a certain location in the memory, it's very likely that we're going to access that same location again. Whereas spatial reference locality means that it's very highly likely that we're going to access a nearby location in the near future. And this has worked well, so that when we miss in the cache, we bring a block of several contiguous locations, data from several contiguous locations in memory, into the cache in what we call a cache block, and then the likelihood is high that we're going to reuse that, reaccess that. So that is why caches work, and the key property that makes memory hierarchies effective. Now, value locality, what is that? Well, it also comes in two flavors: spatial value locality and temporal value locality. What temporal value locality dictates that if we access a certain value, it's highly likely that we're going to access that same value again. Whereas spatial value locality says that it's very highly likely that we're going to access a nearby value, a numerically similar value again. Back in 2010, I just got a new PhD student, and I had a strong intuition that there is a lot of value locality at play. So what I told my new PhD student was that, well, if we could build a cache that was so smart, we don't have to worry about how we are going to do it, but let's think of a cache that is so smart so that it only stores unique values, okay? Then the question is, how much smaller could we make that cache, right? And so I asked my PhD student to derive the miss rate or misses per kilo instruction as a function of the cache size for a conventional cache, okay? And this hypothetical cache, which we call a value-aware cache. And he came back with this diagram that shows it for one, at that point in time, spec 2006 applications. We're going to see the full data set in a while. So what we see on the y-axis is the number of misses per kilo instruction, and how it drops on the x-axis as we increase the size of the cache here, counted in kilobytes, okay? And as expected, with the green curve here, which is conventional cache, we can see how the misses per kilo instruction will drop as we increase the size of the cache. And now the red curve corresponds to the value-aware cache, and as you can see, it drops much quicker, you could say. At 64 kbyte cache, then it drops, whereas for the conventional cache it drops at 1 megabyte. So if we now look at a 2048 kilobyte conventional cache, then we have an MPKI of about 40, and that would be the same as only 128 kilobyte of value-aware cache. So what we can see here is that actually with a cache that is only 16 times smaller, we could get the same miss rate. And that's fantastic, right? But we would need to figure out, of course, how we can build a cache that is so smart so that it could store each value once. So there's a lot of value locality going on here. And we looked at, of course, a number of applications in the spec 2006 benchmark suite. And we could see that on average we got a compression factor of 30, so even much better than 16, which is truly amazing. And we got, of course, this was excellent, data to motivate us to really, laser focus on getting something to work. And to fast forward into the future, and now what is available in a startup company called 0 Point Technology is technology where we at least can get a factor of 4, at play in compressibility. So we carried on to do research on that, and we focused on actually caches to start with, and published a paper in 2014, which is called SC2 Statistical Compression Cache, and that I can tell you a little bit about. So we applied it to the last level cache. So of course there are challenges with compression, and that is that when the processor eventually needs to access compressed data in the cache, we need to decompress it. So we need to do decompression fast, and fast often means that you don't get that much compressibility going on. But we actually figured out a way of smartly using Huffman coding, where we actually we use so-called semi-dynamic Huffman coding. So we actually dynamically look at value, the value distribution in the cache, and forms the encodings from that value distribution. And then we built highly effective, highly efficient Huffman compressors and decompressor accelerators to really make it possible to decompress as fast as possible, and got it to work actually very efficiently. And that buys us improved latency and bandwidth, higher performance, and reduced memory traffic, as we can envision a much bigger L3 cache. And to give you some data about it, so what we have in the diagram here is basically speed up. So we start out from a certain size of a last level cache here, 4 megabyte. I think we used 8 cores or something like that. And then we formed workload mixes called negative impact, that actually the working sets fit in the cache, so compression will not give any benefits. And mixed impact, which is actually that there are in the mix both cache friendly, you could say, applications and cache not so friendly, meaning that they exhibit quite high miss rate. And then of course positive impact, where you have the working sets do not fit into the cache, so you could benefit from a larger cache. Okay, now there are 5 bars. The leftmost bars is a twice as big last level cache. The yellowish is 4 times larger cache, and FPC and BDI was state of the art, the best compression algorithms that were available at that point in time. And then we have the SE2, which is our contribution. Okay, so all over the board we can see that I mean, if we look at SE2, it never gets worse than the baseline. Well, in fact, we're going to look at the worst case. I'm going to comment on that fast. On the other hand, in fact, what happens is that when we go to the mixed and the positive impact cases, our scheme actually performs better than a 4 times larger cache. And that's a little bit non-intuitive. The reason for that is that with compression you don't have to physically make the cache larger, and so when you do make a cache larger, you also make the access time longer. Okay, so actually there is the benefit of gaining higher capacity without seeing, you know, a longer access time to the cache. And that was a little bit surprising to us. For the worst case, we did the experiment that actually we will not benefit from the compression in terms of increased capacity, but rather only suffer from the longer latency because we have to decompress data. And then we saw only, you know, a few percent worse performance, and that would be under the assumption that we couldn't compress anything. So let me talk a little bit about our baseline compressed memory architecture. And so what we see here is actually, and this is what we actually offer in the startup company that was founded in 2016, 0 Point Technologies. So you have basically to the left here typical multi-core chip, okay, with the CPUs or cores or processors or what you want to call them, and connected to an L3 cache. And let me see if I can get a pointer here, maybe. L3 cache, and then, no, sorry, L3 cache is here. And then what happens is that close to the memory controller, we have an IP block, which is called septillion. And what septillion does is to actually, it implements compression and decompression accelerators to actually to make it possible to compress the data in off-chip memory. And if you have the data compressed in off-chip memory, then actually you will increase the effective memory bandwidth. So let's look at the anatomy of this IP block. So when there is an L3 cache miss, then that will be intercepted by this IP block. And the first thing that is going to happen is that there's going to be an access to the prefetch buffer. And if the data is not there, I'm going to come back to what the reason why we have this prefetch buffer. Then we need to access get the data from the memory. And now data is compressed in memory. It means that the location where it is not like in a non-compressed memory. So we need to do an address translation to find the location of the compressed data. That's the role of this address translator. And then we will have a normal request to the memory. But now data is compressed, so when you bring in a 64-byte block, which you do conventionally in response to a cache miss request, then you let's say that we compress the block is compressed by a factor of 4, then you essentially will bring 4 blocks onto the chip again. And these blocks will be decompressed by a decompression accelerator and inserted into the prefetch buffer. So if the processor next access one of these decompressed blocks, you will hit into the prefetch buffer, and you don't have to go to the memory. So you save memory traffic, okay? So the insight here is that bandwidth and access penalty can be reduced by bringing several compressed blocks blocks on the chip in one memory transaction. So let's look at some data here. So here we have the compression ratio of some HPC applications, and as you can see, we get quite good results with on average a compressibility of close to a factor of 2. Also, when it comes to bandwidth expansion, I mean, as I told you, how much we can reduce the traffic, we get 30% less traffic for these applications because of compression. And the impact on performance is quite substantial because we get an improvement of 11%. Across this. And 11% is actually doesn't sound much, but it's actually that plus the fact that we reduce the traffic by 30% means that you can basically reduce 30% of the energy spent in the memory system. So I would say that you get a 10% reduction in power consumption and 10% improvement in performance. So that translates into 20% improvement in performance per watt, which is big deal for data centers that are big power consumers, okay? and that actually one predicts will consume 20% of the electricity by 2030. So that is big deal, really. Okay, so let's move to the next topic, and that's exposing cache hierarchies to software. So a few years ago, I started up a project where we wanted to do cutting across the transformation hierarchy in order to seek efficiency improvement. So what we see here is essentially a part of the transformation hierarchy, spanning from the parallel programming model, the programming interface, you could say, through a resource management layer, which is built from a runtime system, to the microarchitecture. And normally these layers have not talked to each other, and I see a lot of efficiency improvements that come out from that we actually do cross-layer optimization. So I'm going to show you one of a few examples of where that makes sense. First, task-based data flow programming models have been very popular. You might have heard about OpenMP. So you essentially express your parallel computation into a task, and then you can basically build task graphs with data dependencies as arcs in this data flow graph. And you can express, for example, in OpenMP that, for example, like in this example, task A will produce a data structure called A to task B and task C, and the programmer would then express that through pragmas, which is called output A, and likewise task B and task C would actually have that as input. And me and my PhD students saw a lot of opportunities. If people are going to use this kind of pragmas, then you can do a lot of optimizations when it comes to the memory system, okay? So what happens is that you have a runtime system that will construct the data flow graph dynamically, and in doing so you will be able to have a limited future of the future when it comes to memory accesses, and that way making optimizations. So when it comes to architecture optimizations, we typically build them by looking at what has happened in the past to predict the future. But here you can be more aggressive about, and more efficient, more accurate when it comes to predictions. So I see this runtime management of cache hierarchies very much like how operating system manages virtual memory, okay? So it's part of the chip, and communicates with the microarchitecture. So we looked at a lot of, efficiency, a lot of optimizations when it comes to cross-layer optimizations this way. One was to do runtime assisted cache coherence, which I'm going to talk a little bit about, and then runtime assisted deadblock management. So let's first look at runtime assisted coherence management. So we had a paper in 2014, which is called Runtime Guided Cache Coherence Optimizations in Multi-Core Architectures, and where we use these annotations to do optimizations in when it comes to coherence overheads. So let's look a little bit about that. So for example, you could use the annotations output and input to actually do bulk data transfer. So the problem with cache is that you basically bring larger data structures block by block, which actually is very inefficient. So here you could say, I need this entire data structure, and the runtime system, with the help of the program and the annotations, could help to basically propagate that information down to the microarchitecture. You could do prefetching of entire data structures, not only a single block, but rather a whole data structure. And you could, of course, do something that I came up with quite early in my research career, migratory sharing optimization, which is essentially when you have a number of cores that do read, modify, write operations, then you will see a lot of coherence overhead in terms of getting ownership of the data, etc. And here you could also, based on the annotations, send that information down and getting rid of a lot of overhead when it comes to migratory sharing. So we looked at that, and here's just some glimpse of the results. So what we have essentially here is a number of schemes that we looked at. BL stands for the baseline, and then we have a number of optimizations, and we could see here for these applications that we played with, which are typically HPC applications, that by actually connecting using a lot of these optimizations together, which is the last one, which is called prefetching plus self-invalidation and dirty, and they are guided by actually these annotations, then we could get much more efficient, increasing the efficiency, going from 100%, which is the baseline, down to, for example, when it comes to sparse LU, to 40. So that's quite a lot. So cross-layer coherence management can yield significant improvements. Another thing we looked at, published in HPCA 2017, was actually called runtime assisted deadblock management. So what is deadblocks? Well, if you take a snapshot of the cache, then you will see that a lot of blocks that are there will actually never be accessed again. So they just use precious cache resources to, and if we could get rid of them, then we could actually use the caches more efficiently. So again, actually with these runtime annotations, and the fact that the runtime system will build up the task flow, the data flow graph, and have a limited outlook of the future, then we could build heuristics to say that if there is a data structure that is not used, in the future, likely not used in the future, I should say, then we could instruct send a special request to the cache to say, evict this whole data structure, right? State-of-the-art schemes for doing this are prediction-based and based on past behavior. And here we could do it much more accurately, okay? So semantic information plus prediction. So the big insight here is that hardware can only look back, whereas compilers and programs can look into the future. And that's what we wanted to take advantage of. So here is the big picture of things, overview of what we call radar, runtime assisted dead region management for last level caches. So we have the application layer on the top, and then we have the runtime layer and the architecture layer. So we have this, communication between the layers, which is so important, and that's what I advocate and try to, argue for in this presentation. And so the application layer, we have specified the tasks and its region accesses, and then the runtime system is there to actually see if a region is dead after the current access. And if it is like that, then we're going to send basically commands to the cache to basically evict the whole data structure from the cache. So we tried out 3 schemes: look ahead, which use the data dependence graph, and then look back, use past region access statistics, and then a combination where we look at both look ahead and look back, and where we have the intersection of things, meaning that if both are in agreement, then we do it, and if anyone is advocating for something, then we also do it, right? So if we look at the execution time improvements of this scheme, then we will see that bottom line here is that the radar combined did the best, and that we do quite substantially better than the baseline. And do absolutely best for memory-bound applications where we provide significant improvements like Gauss and Jacobi here. Okay, that brings me to the last topic of my talk. Something that I think there is a lot to, and that will happen, is processing in memory, where we actually move computations close to the memory. This is a topic that is not new, but rather there was a lot of interest in the 90s, but it didn't fly because of a number of things. It was not very attractive to implement logic in memory devices. And it would also disrupt prevailing programming models. It was, when we still hadn't went to parallel computing. And if you have many memory chips with compute capability, then you have to go to parallel programming models. But why PIM now? Well, processing memory now. Well, the era of data-centric applications is one. Moore's law is ending. The era of acceleration is emerging. And we have emerging memory technologies. For example, HBM, where you have a logic layer built into the memory device, where it's quite kind of natural to actually build accelerators. Or you could have them also nearby. If you have silicon interposers, then you could have accelerators very close to the 3D stacked memory. Of course, if we look at more exotic speculative memory technologies like resistive RAM, then there's a lot of activity now in looking at how you can do analog computing in these things. So this is something I think will happen. And so we have launched a project at Chalmers where we look at essentially silicon interposer, where we actually think of integrating HBM devices on this to form a fairly scalable architecture with this, and where we actually compute inside or nearby this. Challenges, of course, with this architecture how we're going to map the data structures, and also how we schedule computations across PIM chips to maximize parallelism. So there is a departure from computer-centric to data-centric programming model, and we are launching several projects. We have launched several projects along those lines. So that brings me to my conclusion. So I think we are in a very, very interesting era in computer architecture to deal with more data-centric application, and that puts, of course, even more burden on the memory system. End of scaling laws make system optimizations across the stack very important. I think it's very important to do cross-layer optimizations. And that opens up for optimizations to the software for what we call ninja programmers, expert programmers will be necessary, such as software-defined caches. So future research opportunities for cross-stack optimizations look rich. Thank you very much for your attention.